Well, let's do some practice. So here we have a wonderful test. So this was Math 265, Calculus 3, Exam 2. So this is getting more into our differentiation in multivariable calculus. 7 problems, lots of fun. We're going to have a good time. And of course, whenever we start a test, we always start by writing down our name. We'll put answers, and there we go. We're ready. Off to the races. Number 1. Circle the letter for the correct graph of the level curve of the function f of xy is x squared plus y squared over y minus 4, where the domain, well, everything that doesn't include 4, of course, because you can't, 4 minus 4 is 0, no division by 0, and for the value of negative 2. Now, to be clear what this is saying, level curve is f of xy equals a number. So the question is, where does f of xy equal negative 2? And so, in other words, what's the set of x and y where that's true? So we say, okay, well, what do we do? Well, let's, we have some space down here. Let's work it out. So you can't see it, so you'll have to trust me when I say that our function was x squared plus y squared over y minus 4. So that's our f of xy equals minus 2. Well, of course, we don't like fractions. We try to avoid them when we can. So in this case, let's multiply across. X squared plus y squared equals minus 2 times y minus 4, which is the same as minus 2y plus 8. Now here, we kind of know it's a circle, right? Because you see x squared and y squared. This 2y is throwing things off a little bit. So let's see what it would do. Well, move it across. X squared, no problem there. Y squared becomes plus 2y. Suspicious gap equals 8. Well, of course, what goes into this suspicious gap? Well, we're thinking circle. We should be thinking squares. And so we ask the question, what would complete us? In other words, we have y squared plus 2y. What would we add here so that what we had would be a perfect square? Well, take the middle term, divide by 2, square it, we'd add 1. But I can't just add 1 here, so I'm going to add 1 there. All right, so we are adding 1 to both sides so that our net result is we still are where we started, but of course, not quite that. Because we have x squared, y plus 1 squared, and 8 is 3 squared. And now we're like, aha, we know that shape. We know exactly what that looks like. That's a circle. And we can talk about the center. It's going to be at 0, minus 1, right? Because y minus 1. So at 0, minus 1. And the radius is going to be 3. So we're looking for a circle, radius 3, starting at 0, minus 1. So, okay, pulling back, so we see the pictures. These two circles have radius 2. They're too small. These have radius 3. The center of those two circles, we can roughly eyeball it in. Now, we want it to be at x equals 0, y equals minus 1. So here, that's x equals 0, y equals minus 1. This would be x equals minus 1, y equals 0. So our answer is C. So there we go, our first problem, C. It's a circle. Set your function equal to your value, solve for what it is, clean it up. Void fractions is a great thing to do, and find the picture. And we're done. Off to a great start. Wonderful. Woohoo! Let's keep going. Number 2. Find the tangent plane to the surface x squared plus y squared minus xy minus 2z squared plus xz equals 4 at the point 2, 2, 1. Now, this is a couple of things we say right away. It's like a tangent plane. So, okay, we're after a tangent plane. But there's two camps for tangent planes. There's the z equals f of xy camp. And then there's the f of xyz equals constant camp. And they're slightly different in how you find the tangent plane. In our case, we're definitely in that, we have a function f of x, y, z equal to a constant cam. All right, good. So how does that one work? Well, the thing is, of course, if you need a plane, you always need a point. So that's good. And now the normal, which is our other piece, is going to be the gradient of f at our point. So that's going to be the problem. You have to understand, what is the plane? How do you get the pieces? And in particular, we're really testing on, do you know how to find the normal for the tangent plane to surface of this form? It's about the gradient. The gradient is a really useful tool, so you should expect it to show up a couple of times on an exam. Okay, so, all right, so remember, we're thinking of this part right here. This is our f of x, y, z. If you want to sound fancy and British, you can say f of x, y, z, but you don't have to sound fancy and British. And so you say, okay, let's work this through. We have that the gradient of f is, now the first entry is the derivative with respect to x. So we just start going through. Anything with an x, take a derivative. So a 2x, a minus y, and a plus z, comma. Second entry, derivative with respect to y. 2y minus x, and that's it. Okay. Third entry, derivative with respect to z. Minus 4z and plus x. All right, good. So now we'll plug in gradient of f, 2, 2, 1. Okay, so this is the part where we just have to be careful. So we want 2 times 2, which is 4, minus y, which is minus 2, plus z, which is plus 1, comma. 2 times y, that's 4, minus x, minus 2, comma. Minus 4 times z, that's minus 4, and plus x is plus 2. All right, well, 4 minus 2 plus 1 is 3. 4 minus 2, 2. Minus 4 plus 2 is minus 2. So, and remember, this is our normal. This is our point. So now we have our normal acts like our coefficients. So we can say our plane looks like 3x plus 2y minus 2z equals something. The question is, of course, what goes in that box? All right, well, that's where the point comes in. So it's going to be 3 times 2, 2 times 2, and minus 2 times 1. Plugging in the x, the y, the z. 6 plus 4 makes 10, minus 2 makes 8. So putting it all together, 3x plus 2y minus 2z equals 8. And we're done. That's it. That's the whole thing, right? Because we just needed to find the tangent plane. So the main thing here is to know, if we're in the format f of x, y, z equals constant, that the normal to our tangent plane is the gradient. And that's it. That's the whole key. It all boils down to that fact. Because once we have the normal and the point, we know how to make a plane. Because that's like exam 1 stuff. We're pros at that kind of thing. So, well, great. There we are. 2 done. We're doing wonderful. Number 3. Find the directional derivative for the function f of xy equals sine of xy plus 4x at the point negative 2, 0 in the direction of v equals 3, negative 4. And that's part A. Now there's a part B, which is find the maximum rate of increase of f of xy at the point negative 2, 0. We'll get to that one in a moment. But let's start with part A. Now, when we're talking about directional derivative, there's a couple of things. We need to have a direction, and of course we need to have the gradient. Because in general, we would say, look, the direction, null derivative, which we usually write with a capital D for derivative, in the direction of a vector u, of a function f at a point P. All right, there's a couple things. What's the function? What's the point? What's the direction? That is the gradient of f at P, because gradient is a great substitution for derivative, dotted with the vector that represents our directional derivative. Now, u is good to remember. We want this to be a unit vector. Okay. So we need to do a couple of things. Make sure we clearly have our unit vector in place and figure out our gradient. Okay, so let's talk about the unit vector, because oftentimes that's pretty straightforward. There's two things that frequently happen. One is, from this point to that point. The other one is just like, oh, here's a vector. In this case, we're in the second. Here's a vector. So, is this u? And why not? Well, of course it's not u, because it says it's v. Ha ha ha. No. That's not what I'm getting at. Is this a unit vector? It is the right direction, because it says that's the direction to go, but it's the wrong length. Okay, so we got to fix the length. So we say, okay, well, look, we're really going to take 1 over the magnitude of 3, negative 4 times 3, negative 4, right? Because that's how you turn something into a unit vector. Well, all right, so we have to think for a second, all right, what is this? Well, this is 1 over the square root of 9 plus 16 times 3, negative 4. Okay, so this becomes 1/5, right? 9 plus 16 is 25. Square root of 25 is 5. After you do a lot of calculus problems, you start recognizing, oh, 3, 4, 5. It's a very famous triangle. And we don't have to multiply it in, but the moral here is this is our u. Okay, so now we have our u. All right, let's put this aside. It's like, look at it, we're just sort of expanding. We have the corner, a bigger corner, and now the really big corner, and then of course we'll have our answer. Okay, so now our next layer is, well, we've got to find the gradient. Okay, so our gradient of f, and remember that's going to be our partial derivatives, partial f, partial x, partial f, partial y. So that is, well, here we see an x on the inside. So we have derivative sign is cosine. The inside stays the same, but multiplied by the derivative of the inside. The derivative of x times y with respect to x is y. And then don't forget the derivative of 4x, which is plus 4. And do the same thing. Take derivative with respect to y. Now that goes away, that 4x. Derivative of sine of xy is similar. Cosine xy times the derivative of xy with respect to y, which is an x. So x cosine xy. So that's our gradient in general. We need the gradient at our point. So the gradient f at the point negative 2 comma 0. So everywhere where we see an x, we put a negative 2. Everywhere we see a y, we put a 0. So this would be 0 times cosine 0, because negative 2 times 0 is 0, plus 4, comma, then negative 2 cosine 0. Well, okay, 0, hard to recover. Cosine of 0 is 1, so we end up with 4, negative 2. All right, so we have our gradient at our point, we have our unit vector, and so our last thing is just to dot them together. And remember, when we're taking a directional derivative, our final answer should be a number. Not a vector, a number. And so we're not done until we have a number. And even then, we have to make sure it's the right number, but okay, that's all right. That's what we're doing, is we're following the process. So we take 4, negative 2, dot that with 1/5, 3, negative 4, and okay, so the 1/5 we can just pull out in front. We're going to have 4 times 3, which is 12. Negative 2 times negative 4 is 8. 12 plus 8 is 20. add 5, sorry, not add 5, divide by 5 gives us 4. And we're done. That's it. That is our directional derivative in the direction 3, -4. Okay, wonderful, wonderful. All right, now there's a couple things to check. Check your dot product. 12 and 8 makes 20. 20 divided by 5 is 4. Check your gradient. All right, good, good. Now, part B. So part A was just direct application. Part B says what? Find the maximum rate of increase of the function at the point -2, 0. So really, it's saying, okay, we want to do a max of our directional derivative. Now, how do we find the maximum directional derivative? That sounds hard, but actually what's happening here is we're being tested on properties of the gradient. So the gradient is the tool that helps us find directional derivatives, and it stores lots of information about directional derivatives inside of the gradient. So in particular, it turns out the maximum directional derivative is equal to the magnitude of the gradient. So this problem is really testing us on, do we know this fact? And once we know this fact, we say, oh, well, we have the gradient at our point, so it's the magnitude of 4, -2, which would be the square root of 4 squared plus -2 squared. Well, okay, that's the square root of 16 plus 4, which is 20. And so that's the answer, square root of 20. Wow, that one's not so bad. And it really isn't. It's a conceptual question. Conceptual questions, of course, should test you on, do you understand concepts? By the way, there is something which should be true. Which one of these numbers should be bigger? And the answer is part B, right? Because it's the biggest. So if I had a number here like 10, and I had a number here square root of 20, I know mistakes were made, because there's no way I can be bigger than the maximum. And so it's nice to sort of notice that, oh yeah, 4 is indeed smaller than the square root of 20, because the square root of 16 is 4. So, okay, whew, we probably did something right. That's a good sign. Very promising. All right, wonderful. Well, we're making some really nice progress. We're zipping right along on this one. This brings up number 4. Let f of x, y, z be a smooth function of 3 variables. Smooth, by the way, is just a fancy way of saying you can take derivatives. So if you're wondering, wait, what does it mean by smooth? I can take a derivative. So, okay, that's what it means. Let g of uv be f of u squared minus uv, comma, uv squared, comma, v squared plus uv. And let p be the point -1, comma, 2. All right, now here, when they're talking about -1, comma, 2, this will be a u, comma, v kind of thing. All right, so we're given information. We're given that f sub x at 3 minus 4, 2 is 1, f sub y at 3 minus 4, 2 is -1, and f sub z of 3 minus 4, 2 is 2. And we're asked, find the gradient of g at our point P. Now, let's sort of unravel here. First off, what are we being tested on here? And the answer is, this is a chain rule test. So we're really digging into, do we know the chain rule? Can we figure that out? Now, let's talk about what is the gradient of g. So the gradient of g will be the following. It'll be the partial derivative. So it'll be partial g, partial u, partial g, partial v. Now, how do we know it's in that order? Well, because we put them in the order that we feed them into our function. Since we put u first and v second, partial with u first, partial with v second. All right, so that's what the gradient is. So we have to go through and say, okay, how do we find these pieces? So let's start with partial g, partial u. Now, if we think about what's going on here, we have the following. We have f is a function of three variables, x, y, z. And then x depends on u and v, y depends on u and v, and z depends on u and v. And they actually give it to us in this format here. So it's not, like, wait, what is x? Well, x is our u squared minus uv, y is our uv squared, and our z is v squared plus uv. Okay, there's a lot to unravel here, but this is the key to understand the chain rule, right? The chain rule is how do the variables all relate to one another. We have our top function f that has three pieces. Each one of them in turn relies on two other variables called u and v. And we can just read off the x, the y, and the z. Okay. So here we go. I'm going to write down partial g, partial u. So, well, let's use our colors, right? So we would have what? Well, I'd go x and then f sub x, x sub u. So I'm using subscripts here for derivative. Then fy, f sub u. fz and zu. Whoops. fy, yu, fz, zu. So this is shorthand for partial f, partial z, partial u. And in the other notation, which is called Leibniz notation, it's a little bit easier to unravel and say, oh yeah, it's sort of like, some of the partials cancel. Okay, now, here is something that hasn't been stated explicitly, but let's just make a quick note on the side here that I'm willing to bet must be true, otherwise this problem is hopeless. So that is, when we plug in u equals minus 1 and v equals 2, well, what happens for x? Well, we'd have 1, because that's minus 1 squared, and plus 2, which is 3. Y would be minus 1 times 2 squared is minus 4, and z would be v squared, which is 4, and u times v is minus 2, which is 2. 3 minus 4, 2. Notice 3 minus 4, 2. So we are, in fact, when we plug in our point, minus 1, 2, we do get the right value. So here we go. Let's, there's a lot to unravel here. Okay, so we have f sub x is 1, x sub u. So, all right, we're going to keep writing here. X sub u is 2u minus v. X sub v is minus u. Y sub u is v squared. And y sub v is 2uv. And, well, we're going to have to keep moving up here. Z sub u is going to be v, and z sub v is 2v plus u. All right, so we need all of that. All right, so we know f sub x at our point is 1. Okay, now we're going to times it by x sub u. Okay, so, well, okay. So we should do it at our point. U equals minus 1, v equals 2. What happens? X sub u is minus 2. Minus 2 is minus 4. X sub v minus 1 is plus 1. Y sub u, v squared, that'll become 4. y sub v is 2 times u times v. So 2 times minus 1 times 2 is minus 4. X sub u, z sub u is v, which is 2. And z sub v is 2 times v, which is 4, plus u, which is minus 1, makes 3. Okay, so we have 1 times minus 4 plus f sub y is minus 1. Y sub u is 4. F sub z is 2. Z sub u is 2. Okay, so we get minus 4 plus 4 altogether is minus 4. Okay, now that is that entry. Okay, so we have that this is equal to minus 4, comma. What's in the second slot? Okay, so second slot, here we go. We're going to look at the v's. So we're talking about now partial g, partial v is, we're going to take f sub x, x sub v, f sub y, y sub v, f sub z, z sub v. Okay, so we've put our pieces in. F sub x is still 1. X sub v is 1. F sub y is minus 1. Y sub v is minus 4. F sub z is 2. Z sub v is 3. So we get 1 plus 4 plus 6 is 11. Meaning that our second entry is 11. And we're done. Whew. Okay, all right. Okay, let's catch our breath here for a second. This one, there's a lot, it feels like, is going on here. But if we step back and say, okay, let's frame our discussion in terms of what's the idea. Our problem is a chain rule problem. And so the key was to understand how the variables relate, which is where our picture came from. We had x, y, and z, and so we were able to figure out what is the corresponding point, which is, of course, the point that we suspected from the beginning. We found our partial derivatives and filled them in as values. And so we basically, at this point, if we just follow through here, we had all our partial derivatives that we could possibly want. And then it was just a matter of saying, okay, what's partial g, partial u? Use the tree. What's partial g, partial v? Use the tree. And of course, fill in what you know. And there's our answer. Now, I will say this is a problem where there's lots of potentials for small mistakes. So don't rush it. Go slowly and check. All right, did I take the right partial derivative? Did I, am I in the right setting? Do I have my right picture? It's okay to take a little bit of time on these types of problems because, in the end, we want to get every single point that we can. So, all right, that was a good workout. Let's catch our breath for a second. All right, let's go on. On to the next one. Number 5. Consider the function f of xy, which is 3x e to the y minus xy squared plus 1. Says part A, find all the first and second order partial derivatives of f of x, y. And even without looking at part B, I'm like, uh-oh, second order partial derivatives, Taylor polynomials. And that's what it says. Woo-hoo! All right, good stuff coming. All right, but okay, back to part A. So the good news is there's no big surprises here. You just take derivatives, and so we're not in a rush. Take our time. Enjoy it. All right, so here we go. we'll talk about f sub x. And so that says take derivative with respect to x, and we would have 3 e to the y minus y squared, and of course the plus 1 derivative of that is 0. F sub y, well here, the x is a constant, the y is the variable, so it would be 3x e to the y, since derivative of e to the y is e to the y, and then minus 2xy, and the plus 1 again is 0. fxx is, well, okay, we come up to f sub x, take derivative with respect to x. Well, there are no x's, so it's 0. Well, that was really fast. fxy, which by the way is the same as fyx, because unless you have something really, really crazy, they're going to be the same. And we don't put crazy stuff on exams normally, but yeah, this is definitely not that case. You could pick either one. In this case, I'll pick the first. F sub x, take derivative with respect to y, and that would be 3 e to the y minus 2y. Now, if you took f sub y and took the derivative with respect to x, you'll get the same thing. If you didn't, mistakes were made. And time to catch your mistakes. fyy, all right, well, that would be 3x e to the y, because the derivative of e to the y is e to the y, and then minus 2x, derivative of y is 1. And there we go. There they all are. Life is good. Now, we're ready for part B. Write the second degree Taylor polynomial approximation of f of xy near 0, 1. Simplify your answer. Well, simplify, that must mean something nice happens. All right, well, let's remind ourselves what goes on here. All right, so first off, second degree Taylor polynomial will be what? Well, it would be f at the point, and it's not 0, 0. Pay attention here. It's at 0, 1. So we gotta be careful here. And then plus f sub x at 0, 1 times x minus 0 plus f sub y at 0, 1 times y minus 1, because we're at y equals 1. And then we get into the second order pieces. We're going to get 1/2 fxx at 0, 1 times x minus 0 squared. And the 1/2 is to compensate for the square. Plus fxy 0, 1 x minus 0 y minus 1. Now we don't need the half here, because notice we're not squaring anything. And so the square is to compensate for the half. You might, well, how is it compensating? Well, if you were to take derivatives, the 2 comes down. So you're compensating for that 2 coming down. Well, here there's no 2 coming down, so we don't need to do anything like that. And then plus 1/2 fyy at 0, 1 and y minus 1 squared. Okay, so that's what we have to find. So we have to find these values. So let's come back up, and we have some space here. Let's actually write what these values are. So let's start with f. Plug in x equals 0, y equals 1. So notice you'll have a 0, a 0, and a 1. So that's pretty simple. All right, now we'll come into f sub x at 0, 1. What do we have? Well, we'll get 3 e to the 1, which is 3e, and then we're going to subtract 1. All right, what about f sub y at 0, 1? Well, we're going to get 0 and 0, right? Because anytime there's an x downstairs, it goes away. Well, that's pleasant. F sub xx at 0, 1 is 0, just because everything is 0. It doesn't really matter. Fxy at 0, 1 Well, that's 3e minus 2. All right. Fyy at 0, 1, well, is 0 and 0. So that goes away. So actually, we see right away that their fy term goes away, our fyy term goes away, and our fxx term goes away. Wow, that's lovely, lovely. Okay, so what do we have? What's left? Well, we have the following. We have our f of 0, 1, which is, let me move this up, f of 0, 1, which is 1, fx at 0, 1, so that's 3e minus 1 times x. And then we have our fxy at 0, 1, which is 3e minus 2 times x times y minus 1. All right, now the age-old question. It says, simplify your answer. And so you might ask, well, how do you know if it's simplified? That's hard to say, isn't it? Well, we could maybe do a little bit here. It's always hard to know when they say simplify your answer, just like, how far can we go? Well, I will say, notice here, this is the same as xy minus x. So that's probably says, well, let's at least do that. So that way they'll say, hey, this person, they did a little bit of simplifying. So this becomes 3e minus 1 times x. And we have a 3e minus 2 times xy, and a minus 3e minus 2x. Oh, well, wait, those could be combined. So let's think about that. We have 3e minus 1. You can do it on the side here. 3e minus 1. Subtract 3e minus 2. The 3e's cancel. Minus 1 minus minus 2 leaves us with just 1. So we could say, oh, this is 1 plus x plus 3e minus 2 xy. And yeah, I can't think about anything that we could do to that to make it simpler. So there we go. 1 plus x, 3e minus 2 times xy. All right, beautiful, beautiful. That's not a bad answer at all. All right, well, that's number 5 done. Let's keep moving on. Moving right along to number 6. Find all the local maxima, local minima, and saddle points of the function f of xy equals 3y squared minus 2y cubed minus 3x squared plus 6xy. Ah, beautiful. Mwah. I love these problems. What are these problems? These are find all the local maximums and saddle points. There's no limits on the domain. So really what's happening here is we're going to talk about fx equals 0, fy equals 0. So these are, in other words, these are our critical points. Okay, so we're going to find critical points. And it does our favorite thing, 2 equations and 2 unknowns. Okay. All right, so let's talk about our 2 equations. So we start with f sub x. And we say, okay, derivative of that. Well, derivative with respect to x, that goes away, goes away. We get minus 6x, and then plus 6y equals 0. Now, notice this is actually a really simple equation. Because what does it say? It really says, oh, y has to equal x. Because you can move the 6x across and divide by 6. Okay, well, that's good information to know. How about f sub y? Well, we're going to get 6y, then minus 6y squared. That goes away. And then a plus a 6x equals 0. But we know that y equals x. So one thing we can do is we can divide everything by 6. And we say, okay, well that says y minus y squared plus x equals 0. Replace y by x, and you say, oh, y and x really becomes 2y. So 2y minus y squared equals 0. Or you can say that's the same as y times 2 minus y equals 0, which says y has to be 0 or 2. Now, remember, since y and x are the same, we have to get points. So we're going to say, oh, y equals 0, and we're done. No, what's the corresponding x value? So our critical points are at 0, 0, and at 2, 2. Now, are we done? We found where things happen. What haven't we done? We haven't said what they are. Are they maximas, minimas, saddles? What are they? Well, that leads us into phase 2 of our problem. What is phase 2? Well, phase 2 is classifying. Okay, so here we go. Now we're into our classifying. And for that, we have what we call the second partials test. So let's just write down a couple of things. So, well, what do we have? We're interested in this value, fxx, fyy, subtract fxy quantity squared. That's what we're after. We want to know, is this positive, is it negative, or is it 0? Now, if it's negative, well, we're definitely done already. It's a saddle. If it's 0, well, we don't know what to do. Yeah. Other tests, I guess, is what we'll phrase here. Don't know what's going on. But if it's greater than 0, well, then we have to dig deeper. Because if it's greater than 0, it means it is a max or a min. And essentially that philosophy is look at a slice. So then you say, okay, if xxx is positive, then we're at a min. If xxx is negative, we're at a max. And that basically goes back to the second derivative test in Calc 1. Okay, so here we go. We got to write some stuff down here. So we have fxx. So come back up here, is minus 6. By the way, this automatically tells us what? We're not going to have any mins. Right? Did I get this right? If xxx is positive, yeah. If xfx is negative, it's a max, right? Because fxx is always negative. So we can never have ffx be positive. No mins. So it's maxes or saddles or, I'm pretty sure it's not going to be in, All right. Sorry, I digressed. All right, fxy. And of course, if you've been ever watching my videos, you know I do digress quite a lot. All right, fxy is positive 6, and fyy is, well, okay, so it's 6 minus 12y. All right, so here we go. What do we have? So at the point 0, 0, we have that this fxx, fyy minus fxy squared is equal to, well, we have minus 6, positive 6, and then we're going to subtract 6 squared. Okay, so this is very negative, super negative. And so our conclusion is that 0, 0 is a saddle point. All right, good. Now, what about the other point? At 2, 2. Well, you have fxx, fyy minus fxy squared. All right, so we have minus 6. Then we have 6 subtract 12 times 2, right? So 6 subtract 24. Whew, okay, that's a number, right? Negative 18. Then we're going to subtract from that our 6 squared. Now the thing is, we don't actually need to know the value here, right? We just need to know the sign. So this is a positive number, and it's pretty big. It's 108. This is 36. 108 subtract 36 is positive. In case you're wondering, it's 72, but we don't actually need to know that. We just need to know the sign. So it's positive. So we say, oh, now look at the slices fxx and fyy. But we know since fxx is negative, we are at a max. So 2, 2 is a local max. And we're done. All right, so this is, whenever it says local max, local min saddle, you know there's sort of two parts. First part is that the partial derivative is equal to 0, solve. Second part, we're going into the second partials test. This expression fxx, fyy minus fxy squared, and we're looking at the signs of various pieces to help us distinguish what's going on with our different points. And good, nice. I love these problems. I'm always partial to 2 equations, 2 unknowns, so it's a great time. And good. Just one problem left. We're almost there. Let's go. Let's finish it up. Our last problem, number 7. We're asked to find the point on the ellipse x squared plus 6y squared plus 3xy equals 40 with the greatest x coordinate. And it says, hint, maximize the function f of xy equals x. Now, it may not be totally obvious that, in fact, this is an ellipse, but we don't have to prove that. They told us it was, so we're just going to go with it. We trust the people who wrote these problems. Say, okay, so we have our point on an ellipse, and we're trying to maximize the function, and they even gave us a hint. So what is it? We're trying to maximize with a constraint. So you might think of this as constrained optimization, but for that, we really say, aha, this is Lagrange. All right, Lagrange multiplier problem. So what do? Well, we just have to remind ourselves how it works. So if we think about this, we'll call this function for a second g. What happens is that the gradient of f is some multiple of the gradient of g, and our constraint is satisfied. So those are our 2 conditions that need to be true. The gradient of f is a multiple of the gradient of g, plus we're on our ellipse in this case. Okay, so we go through and we set up our system of equations. So we say, okay, well, what is, now let's dig into this. This is f sub x equals lambda g sub x, f sub y equals lambda g sub y. So in our case, we have f sub x is 1. That is equal lambda. G sub x would be, well, it'd be 2x and then 3y. F sub y is 0. There is no y. That has to equal lambda. G sub y, well, that's 12y and 3x. Okay, good. So we have our 2 equations here. Now, we have a couple possibilities, and we have to explore both possibilities. So look at this for a second here. Notice how we have that 0 equals a product. So there's 2 cases, namely lambda could equal 0, or that 12y plus 3x could equal 0. Now, could lambda be 0? And why not? It can happen. So don't just say, aha, well, no, it can never happen. Oh, because it can, but not in our case. Because notice, if lambda were 0, we would get that this expression up here would have 1 equals 0. So this is impossible. Can't happen. So we know that 12y plus 3x has to equal 0. And this is the key. So what happens in these problems is when you have your gradient of f equals lambda gradient of g, what you're secretly looking for is a relationship between x and y. Now, one way to do this is, when in doubt, solve for lambda. Well, in this case, we couldn't solve for lambda. Another way is just say, oh, hey, what are some consequences? So in this case, we say, great, well, 12y plus 3x equals 0. Another way we could write this is x, right, we move the 12y across, divide by 3, is negative 4y. So this is going to be key idea. So from our gradient of f equals lambda gradient of g, x has to equal minus 4y. Now, once we have that relationship, we come in and we plug that into our constraint. And so we say, okay, where are we at? Well, we have that x squared plus 6y squared plus 3xy should equal 40. But we have x equals minus 4y. So we replace everywhere there's an x, we put a minus 4y. Minus 4y squared plus 6y squared plus 3 times minus 4y times y equals 40. Okay. Well, we 16y squared, we start multiplying this out. 6y squared, and then we're going to get minus 12y squared equals 40. And, well, okay, 16 plus 6 is 22. Subtract 12 gives us 10. 10y squared equals 40, or y squared equals 4, or y equals plus minus 2. Now, at y equals plus 2, what do we get? Well, we come here, we see x equals negative 8. And at y equals minus 2, because x is negative 4 times that, x equals positive 8. So our max mins, if they occur, and you always have to be a little bit careful here because weird things happen, we are guaranteed there's going to be a max or a min. And the reason we're guaranteed is because there's a technicality, but basically it's because we have a nice shape. Nothing goes off towards infinity. And our function we're dealing with is nice. So basically there's no infinities involved, so everything's good. So max min happens at one of these points. And now we're like, great, well, which one of these has a larger x value? And well, the good news is it's pretty easy to figure that out. We just say, oh, it's at the one where we have x equals positive 8. And so the point on the ellipse with the greatest x coordinate, and remember, it's the point, is at the point 8, comma, negative 2. And so that's it. Wow, that wasn't so bad. And I actually like Lagrange multipliers. It sounds scary, and but once you get the hang of them, they have a really nice flow. And so the way I like to think of the flow, gradient of f equals lambda gradient of g, either solve for lambda or find the other way to get a relationship. And your goal is, from gradient of f equals lambda gradient g, how do x and y relate? That's your goal. Add another way that x and y relate. Combine that with the way x and y relate by your constraint. Solve for your points. Plug in. And life is good. And so there we go. That was our final problem. We made it. We're done. Woohoo! All right. Well, I love multivariable calculus. It's one of my favorite subjects. I always look forward to teaching it. I hope you're enjoying it while you're taking it. And let's all have a great time and do well and pass it. The class on our first attempt, because there is such a thing as too much of a good thing, right? So just one and done. Let's get it through. And good luck, and I'll see you again. Bye.